Hi, good evening, everyone. So welcome back to Plan 258, right? Okay, so our discussion today is about ideal flow network. Okay, so this is the agenda. Right. So we'll discuss about dynamics and then and signature, so mainly about this one. And then this is the summary about how to apply IFN. Okay. And if we have time, then we can continue with the IFN prioritizations. This is optional. Okay. So I have seen some of your assignments. Not everyone participated yet, but I think it's more than half. Okay. Is there any difficulty in making that assignment? Of random? Yes, Lay.
So I would like to ask regarding our assignment because I just want to confirm that if we convert ideal flow network to stochastic and we prompt it if it's pre-magic, it says that it's false. Am I right? Or can I?
Okay,
you
you can share your screen.
So so I'm in an iPad, so I don't know how to. I'll
Oh,
try to. I'll try to connect on the
okay.
or send a screenshot in our meeting. But when I did this stochastic matrices and tried to prompt it if it's free magic, the answer is false.
Really?
Yes.
Uh,
I'll try.
so please check the value so that we can see.
Also. But that's the I think the total is okay. I'll try to. My my computer isn't working, but
Okay.
I'll try to check it in my
Okay, if
my
you can screenshot, then you can share.
yes.
We can check the actual values.
Yes. Also, sir, may I confirm the LCM for the base?
Okay. So that one is possible. So
Yeah.
let, let me show you can I share my screen? Okay, let's start with simple. Um, so I will share with you next cell. Okay, let's start with simple. So we have n underscore random network, right? Capacity matrix. Say you have, for example, 4 by 4. Is that okay? So we make the size 4 by 4. Okay, and you just highlight using arrow. Okay, and then you click this one, the formula bar. Okay, and then press together Shift Control Enter. There. Okay. So you will get a random capacity matrix. Okay. So if you want, you can format it, for example, make it smaller, or if you want, you can change this to 3, for example. So this is the random capacity matrix. Okay. Now, if you want to create ideal flow network, okay, let's start with creating the stochastic matrix first. Say, because this is random, that means I will put here every time I press calculate, okay, it will create new values. Okay, so probably we don't like that. So okay, let's put this random values. Okay, copy and then okay, home I will paste it as value, okay, so that it will not change anymore. Okay, so we will change this manually. There. So when we paste as value, can you see? Now the value is actually no longer random, yeah? So if you change this, it will not change. Okay. Now, once you have the stochastic the capacity matrix, see, okay, you can calculate this manually if you want. So I will put manually here so that you can see. Okay. First, if you want to get manual stochastic matrix, all you need to do is get the sum. Okay, so I will get the sum. This, okay, to the right, right? So then I will put the stochastic matrix here. Okay, all we need to do is just this one itself divided by the sum of its row. Because we want to divide by the sum of its row, that means in here, in this case, the column G should not change. Okay, so I will put $string here. Okay, so in that case, now we just copy. Yeah, this is the stochastic matrix. Yeah. So of course, when you sum the stochastic matrix, it will become 1. Yeah. So this is the stochastic matrix. Let's color it blue. Okay. So instead of doing this manually, you can also do using function. Yeah? So n capacity to stochastic there. Okay. So you get exactly the same value. So all you need to do is copy this and then shift control enter. Yeah. This ones look like not the same, but it is actually the same because I reformat this. No? See, exactly the same. Okay. Now, once you have the stochastic matrix, you need to know the total flow. So kappa is the total flow. So let's put any value here. So I will put, for example, what is
100, sir.
100. You want 100? Okay, let's put it 100. Okay. So this is again, this is manual. So we need to put this. So now we can get the F, yeah, ideal flow network. Now we can get n underscore the capacity to ideal flow, right? So we have the capacity matrix, the one in yellow, and then kappa is the one in here. Okay. Again, we just highlight, and then you need to use the same size, so 4x4. Okay, press that and then shift control enter. Huh? So let's make it so that this one become 5. Okay, so we have this value. So if you put the sum in here, okay, right, and then now I have the sum here. Okay. So the sum of each column should be exactly the same as the sum of each row. Okay. And the sum of total must be exactly the one that we specify. So let's color this so that you will know that this is actually a matrix that we want. Okay. So of course now you can test, okay, whether this is actually ideal flow or not. So n underscore is premagic, we are asking. Is premagic. There. So we press this and test. Of course, it's premagic. Yeah? It's premagic, right? And one.
Stochastic. Do we also prompt the pre-magic or just for the ideal?
Of course, the stochastic will not be premagic.
Oh,
You can check.
thank
Yeah.
you, sir.
So the stochastic will not be premagic. So n underscore is premagic. It is false. And false. Right? Why? Because if you sum, let's do the sum here. If you sum this is all 1, but the sum in the bottom is not. And I will just copy this up. See, the sum is not the same, you know. So when you have this, okay, let's follow this with the PVC. The sum is not very much, actually, it's not the same, right? So in fact, when the sum of the row and the sum of column is exactly the same, you will get what is called doubly stochastic, double stochastic. Okay, and that's a special matrix. Okay, okay, so it's very much it. One more, the one that important is irreducible, yeah. Okay, so this is one test that is very important. So n is irreducible. Okay, of this one should be yes. Right. So in that case, this is ideal flow. So of course you can also test immediately. Yeah? So is ideal flow, right? One is easier. Yeah, of course, also do. Yeah. Now, your back to your question. How if I want to get the scaling? Yeah. So I want to get the kappa here instead of putting 100. All right. So this is what you will do. Okay. So I will put this into fraction. Go here, go to the fraction. Can you see? Oh, I need to reformat this. There. Okay. Can you see this in the fraction? So if you look at the fraction, okay, let's get the LCM. Yeah? So this one is, what do you have there? 3, 3, 7, 21. 3, 7, 21. So LCM is probably 21, is that correct? Okay, let's try. What will happen if we use 21? Oh, still I have multiplied by 5. So in that case, I will put here 21 multiplied by 5. So I got the exact integer. Is that okay? Okay.
Thank you, sir.
Yeah. So
Um,
yes, go.
I just want to confirm, sir. I provided the image on the chat box for the basis network. Because at first it's not showing common denominator. It's okay if it does that, or it.
Okay, so basis network is basically as simple as this. So once you have this f, okay, whatever number that you can put here, so all you need to do is, sorry, this one divided by the total. Okay, this is already basis network. Okay, so because we divide by one cell, so you need to put this with the double dollar string, isn't it? And then copy, right? There. So this is basis network. And you can check, okay, this is still pretty much the same. And now let's put the sum. Okay, this is exactly the same, yeah. Only the difference is now the total is 1. Okay. So of course you can, instead of doing manual, you can also use the function, yeah. So n underscore basis network, yeah. The basis network of this one, okay, the same thing. So you can just put 4, there. You get exactly the same thing, yeah. So if I remove the function here up to the original, you will get exactly the same. Yeah, because internally is the same. Okay. Okay, who else ask question? France?
So does it matter if we use capacity to ideal flow or stochastic to ideal flow? It produces the same value, I think, but there are two functions, capacity and stochastic to ideal flow.
Yeah, very good question. So the create, well, what we want is actually from capacity, okay, we approximate into stochastic matrix. Okay, so the capacity matrix is just any number that you can put there. So in the traffic paradigm, we talk about the number of lanes here. Okay, and then the actual ideal flow comes from the connection between stochastic and the ideal flow matrix. So now in the function that I make, okay, you don't need to go to the stochastic. You can go directly from capacity directly to ideal flow. Okay, that is to simplify only. But the actual computation internally, you need still to compute the stochastic. But we can bypass the steps using the function. Okay, so in this function, capacity to ideal flow, right? That means internally it has stochastic matrix computed.
Mm.
Okay, so I don't show, but the actual theory of ideal flow matrix is actually come from here, not include the capacity matrix itself. Okay, but for your convenience, so we make it bypass directly.
I see, sir.
Okay,
Thank you.
yes, Pearl.
Hi, sir. I would like to ask regarding my work yesterday because I was working on my MacBook, and then when I tried to generate the Premiere network, it's showing zero. The whole matrix is zero. I'll show you the picture.
Okay, okay. I will put you as co-host. Oh, you are already co-host. So I will remove my share. Go. Are you sharing your screen or?
I'm sending the picture, sir. It's still uploading.
Okay.
It was already uploaded, sir.
Okay. Let me check. Okay. So what's the problem?
The Premiere network is showing zeros on all the matrices. I tried to do it like 5 times, generate a new sheet, and then it keeps on showing like this. So what I did is I tried to borrow a Windows laptop, and then when I did it there, it worked. I don't know why it's not working well on the MacBook.
Really? Only in the MacBook not working?
Yes.
Oh no. But in Windows is work, the same number.
Yes.
Oh, I don't know about that.
Mm. I tried to remove the add-in and then added it again, but it's still showing the same thing. So yeah, I tried it on Windows instead.
Okay. So thank you for the feedback. So I really don't know that. Anyway, so if you have difficulty with the Excel add-ins, so I give you another alternative. Okay.
Okay, sir.
Okay.
Thank
So
you, sir.
yes. So here is the alternative for you. Okay. You go to in Refoled 2. Okay. Let me go to Chrome. Okay. You open your browser. Okay. And can you see? You go to this tutorial, Refoled tutorial. Okay. And then there is an ideal flow network, can you see? And you can actually get the Premier network here. Yeah. In the lab, Premier network, and also composition decomposition. Okay. Can you see that? So here is the capacity matrix. Okay, so you can also do random values here. Maybe I should make it smaller. The screen is so bad. Can you see? So this is the okay, so this is the random capacity matrix. Okay. Of course, you can save and upload if the matrix that you want. If you cannot see the pattern, you can click this one. Now, to use this is easy. Okay, you can create your own. Say, for example, I add here one. Okay, and then you click this cut cycle to get all the cycle that you have. Okay, so once you have the cycles, okay, you click this add premier cycle to buffer, the one in yellow. There, this one is your prime premier network. Okay, so okay, after this we will discuss about this signature, yeah, so that you can understand this better. Okay, so you can create random capacity matrix here, and then get a cycle, and then add premier. Of course, this is only one cycles. Okay. Exactly the same as the Excel add-ins. So just in case you have problem with the Excel add-ins. So up to here, is that okay? Gabriel, Ray, you want to say something? Okay, so MacBook still have problems, so sorry for that. But I give you alternative, so you can still use this the lab tools in online. Okay, so if you are familiar with Python, that is also in GitHub, so you can just download and run Python. Okay. Yes, Ray, you want to say something?
Yes. Yes, sir. Hello. Similar with Pearl, I'm using a MacBook.
Okay.
I'm encountering problems as well. So can I share my screen?
Oh, sure. Yes.
So whenever I generate a random capacity matrix, um, no zeros are showing up. Is that normal? Or
Okay.
it's always
Let's start here.
it's always
That's strange. Okay, maybe the way you do. Can we start in any cell here in P21, for example?
okay.
Okay, and
So
equal and underscore random capacity. Yeah. Okay, close it. Enter. Okay, and then now you highlight. Okay, should be in the same size. 1, 2, 3, 4, 5, 1, 2, 3. Okay, so then you go to this, and then I don't know in Mac how do you call the same Control Shift Enter.
there.
That's
It always generates non-zero numbers. So
yes.
I'm not sure if that's correct? Or
That's super strange. It
yeah.
seems like you are copying all rather than doing the matrix.
Oh,
This will happen if you are doing it as copy of one cell to all rather than you do matrix operation. This is not matrix operation, but you just did copy operation, not matrix operation.
but essentially, all cells in this
So
are
please check how to do matrix operation or array operation in Excel in Mac. So I'm not sure about that. So please check. Okay.
okay, sir.
What you are doing in here is actually copy operation, not array operation. That's why you get this.
Excuse me. Can you try Control U and then Control Shift Enter? Because I had that same problem too with my Excel.
So that
So you
one,
select 5 by 5,
Correct.
5 by 5, then Control U, then Control Shift Enter. When that is popping up, the copy paste, you go to System Settings. At the lower, go to your Mac System Settings. That's a new feature of Catalina. Go to your Mac System Settings.
And then
Go to Keyboard. And then Keyboard Shortcuts. Then go to Keyboard and uncheck the Show Contextual menu.
okay.
Then done, and try it again. It took me a couple of hours figuring that out.
Okay, let's try it
So,
again.
5 by 5, then Control U, then Control Shift Enter.
there.
Okay, that finally
Okay.
works.
So,
Then
okay.
you're sure if you're sure it's a array if you can see the function in the top
There.
Yes. There's parentheses.
Correct.
Yes.
Right.
This is correct. Now you get the array, and you cannot change the part of the array.
Okay. Thank you so
Okay.
much, Franz.
Yeah. Thank you, Franz. So the actual problem is you copy instead of doing array operation.
Okay.
Okay. Right. Next. Anyone else still have problem? Okay. Good. So in that case, let's start with the lecture. Okay. So last meeting, I showed you about the power dynamics, right? So we have the slide of power dynamics. Okay. So, and I want to skip a lot of things here, okay, and then show you just the application. Okay, you can read by yourself all the other details. Okay, and then okay, so if you want to apply this in your own project or application, I provide you with that template of AI, so you can also use. Okay, so all you need to do is just change this application name and your code. Okay, next, now this is already discussed with meeting, right? So here first, there is a 3 special integer of IFN, but all you need to do is to remember just 2. Okay, one is called cardinal IFN, the other one is premier IFN. Okay? So cardinal IFN is basically equivalent. Okay, IFN, that means from the stochastic matrix you get the from the capacity matrix you get the stochastic matrix, right? Okay, once you have the stochastic matrix, when you create in cardinal integer, cardinal IFN, it will not change. The stochastic matrix will not change. Okay, so Sometimes because the LCM is very big, if your matrix is very big, the LCM become very, very big. So in that case, you cannot get the cardinal IFN. Okay. Or there's an error because of that. So that's why this is an approach, yeah? Close to that stochastic matrix, but not actually preserved. Yeah. So integral by IFN is just approximation of the cardinal IFN. Okay. So now, if you only have network structure which is just binary, okay, so your matrix is just 0 and 1, okay, so you don't know the actual strength of influence, so you can use premier IFN, okay, you just remember two, okay? One is if you know the strength, you use cardinal IFN. If you don't know, use premier IFN. So okay, so this is an example. So you have a capacity matrix like this, okay, and this is the stochastic matrix. If you calculate, okay, you can get the cardinal network, this one, and this is the approximation integral network, and the premier network always the minimum, yeah. So you can see from the total, and the one in blue here representing the sum of row or the sum of columns. So you can see this is pretty magic. Okay, this is your assignment supposed to be. Okay, now we can also calculate, okay, from these numbers, okay, so that you can get exactly similar comparison. So in Premier here you get 1, 2, 3. Yeah. So how about here 76, 49, 72, 40? That's difficult to compare to the Premier network. So in that case, you can create what is called relative power, yeah, or relative values. Basically, you get the sum of row or the sum of columns. Okay, it is the same, right? So the sum of row, okay, and then you divide it by the minimum. Okay, so in that case, you will get the minimum, of course, become 1. Okay, so that you can compare. So sometimes, okay, when you just do prioritization, the rank will be exactly the same, okay, but the power actually reduced. So using relative power, you will clearly see how much is changed. Okay, but if you just use rank, you don't see that. So that's why we have this relative powers to see the actual strength of the power. Okay, so with that, we can create what is called a check and balance system. Yeah. So we ensure that there is no single component or single entity that dominate or operate without accountability. Okay. So there is always some kind of monitoring or overseeing that regulate the whole system. That is the meaning of check and balance system. Mathematically, check and balance system is basically IFN, which is irreducible pragmatic. Yeah. So we can apply this, okay, for government, business, family, university, whatever entity that you want to check, okay, the actual system. Okay, so in this case, you create distinct entities or factors. So remember here, the nodes represent entities or factors. Okay, and then you put those nodes, and then you put how one node influence the others by creating the arrow. Okay, so once you have that, okay, so this one you can just read. Okay, so the node represent the entities here, agent or factors. Okay, in the strategy, probably you don't put the entities or mix between entities and factors. Okay, and then the links here represent influence, inform, control, feedback. monitor, or supervise. Is that okay? Okay, so now the strength of the link flow, okay, so the flow in the link represents the strength of influence. Yeah? The flow in the node represents the power. Okay, the step is simple. So you create the nodes and then you create the links. As simple as that. Okay. So, and then okay, and once you have the node and links, okay, the next step is to make it irreducible. Okay, so once you make it irreducible, then you can calculate the ideal flow. Okay, once you make the ideal flow, there are many analysis you can do. Yeah, well, the simplest is Markov. So we check the nodes, strength, and link. Later we will discuss about signature. That means you can get the cycle analysis, the coefficient, the pivot. Okay, and then you can also do what if scenario comparison, or if you want, okay, you can do find optimization. Yeah, find the best structure and the strength. Okay, so the most important part, okay, of the strength, the step is actually to create irreducible matrix which is strongly connected. Okay, so now if your network is actually have source or sinks, okay, that means your network is incomplete. Meaning the way you create the system is still not yet complete. So that means you need either to add nodes or you need to add links. Is that clear? So why? If you have the source node, that source node will become dictator. Yeah, in the jargon of power. So this is dictator. That means this source node is unchecked system. Okay. Now, if you have sync node or sync component, okay, basically you can this sync component or sync node are redundant. So you can delete the sync node, or you can remove or ignore. It will not affect the system anyway. Okay, so in that case, you don't want this. Okay, so then to create a strongly connected network, you add other nodes or you add other links. Okay, or you want to remove. That's also possible. Okay, so here is the example of weakly connected. Last week we discussed about this. Okay, and then you can make it strongly connected. Yeah, the way this is another incomplete system. Okay, basically we have the management here as the source node. So practically this is useless. If we all of these are useless now, except the management, because the customer is sync node, so we can just remove because they are redundant. Okay, once you remove the customer, what happens if you have this marketing and sales become the sync node? Again, you can remove the product is become removed. So all the sync node, when you remove, eventually you will get only one, which is the management. So the system is practically just one node with this management. Okay, so that's why this is incomplete system. Okay, now this is another example of incomplete system. You see there is always source and sink. Okay, and then to make it strongly connected, all you need to do is, okay, adding up communication, yeah, link. Okay? Either you add the links, yeah, or you can add node. Yeah, so you can add node. Usually, the one that most people forget is actually the target or the goal node. Yeah. So if it is in the business, the customer, they forget to include the customer. Yeah? In politics and in transportation, you forget the citizen or the residents, the one that's supposed to get the benefit of this project. You did not include. Okay. So and construction, okay, the building itself. Yeah. Remember, agent not necessarily human. It can be the buildings. Yeah. So you can put that as a node. Once you make it into all this complete, so you can start to see, okay, this is a simple example. If I have only owner and contractor, the owner becomes the source, the contractor becomes the sink, okay? Then to make it strongly connected, I simply add up communication link here. So this is already a two-way communication, okay? The same thing here. This is incomplete system because you have a source node and sink node in the worker here. So how to make it strongly connected? Again, I can just simply add communication link up, right? So now this is become irreducible system. Simple, right? And the same thing here. So if you have the this system on the left, okay, you can also add another node, yeah, with these buildings. In this is the output, right? So in that case, from the building, you go back to the owner. Yeah, that means the result of the building will become the feedback to the owner. Is this until here? Yeah. Yeah. So we are talking about long-term effect. Okay. So this is what you need to do. Yeah. So you add communication link or you add some other node. Yeah. Usually the output target node. Once you can make this, so you can create what is called irreducible or strongly connected network. Once you know the strongly connected network, all you need to do is to input this network as 0 and 1 capacity matrix, okay, and then just calculate the premier network. Easy or not? Do you want me to demonstrate or? Okay, so the same thing here, right? This is an example, okay, in business setting. So which one is better? Yeah, the left graph or the right graph here? Yeah, majority people will say, oh, maybe the right graph is better, but in fact, this is no. Yeah, if you want to prioritize the customer, the left graph probably better than the right graph. So how do I know? We compute. Yeah, we compute the premier network of these two graphs. Okay, so and most people often mistakenly that a structure organization. You until now you can always see something like this, right? So it's a tree diagram, but this kind of tree diagram is basically reducible structure of dictatorship. No, so it is incomplete accountability, no oversight of the top position. So this is incomplete structure. Okay, so the correct organizational structure must be pragmatic and irreducible. That means you need to create balance, yeah, in the system. Okay, so that means you can add who will be the central focus of the affected people here. Okay, then from there you can put link back to the top one. Okay, so with this we can start to compute. Yeah, so again, yeah, once you create the network, okay, and then make it irreducible, okay, then all you need to do is to check, yeah, if your if your capacity matrix has certain strength, so you know the strength, okay, then you can use premier network. Yeah? If not, you can use cardinal network. Okay. So once you have that, those network, okay, then you can actually search, yeah, search for a check and balance system. What is the ideal one? The ideal one is, of course, equal balance. Okay, so equal power is the best. Okay, so but IFN is just a tool to simulate, to predict, and to control. Yeah. Okay. You cannot control unless you know how to predict. So you predict first, and then you change the input in order to get what you want in the output. That is called control. Okay. So with this, okay, let's give an example. Okay, so in the family, you have this is dominant father here, so you need to make it into a strongly connected network. Once you make it into strongly connected network, then you can compute, yeah, because I don't know the strength, yeah. So in this case, I just compute it as a premium network. Okay, let's do this in Excel. Is that okay? Okay, sure. Then you can practice if you want. Let me show this in Excel. Okay. Okay, so I have a new sheet here. Oh, I did not share it. Can you see the Excel? So I have this scenario. Okay. So then I can put here A, B, C, D, right? So let's say A is the father. Okay. This one is the mother, right? This is the son, and this is the daughter. Okay. So then again, yeah, A, B, C, D, right? So then all you need to do is to create the so the father to the daughter. Right? So A to T, 1. Is that correct? Okay. And then from the mother, go to the father. Okay, so see, base transpose. Right? Yeah. Okay. So from the mother, go to the father. So again, 1, right? And then from the son, go to the son is here. Go to the mother. So 1 here. And then from the daughter, go to the son. There, 1 here. Oh, there is one more. From the mother, also go to the daughter. There. So this is the capacity matrix. Yeah. Okay. So this is what we have. Okay. So let me copy this. And then I need to change this to into Premiere. Yeah. F star. So all I need to do is to n underscore Premiere, right? Premiere network. Okay. So highlight and then shift control enter, yeah. Then I get the Premier network. So this is the result. So I will put it in different color. Now, if I want to get the power, I need to sum. Okay, so the sum here. Oh, what happened? There. Yeah, so this is the sum. Okay, so then you get the sum of column. So this represents the power, huh? Okay. Is it exactly the same as the slide? Yes, Finn, you want to ask something?
Sir, the assignment of the flow value for the son and daughter, which is 2, is it arbitrary or
That's
is it
a
regular?
very good question. Yeah. So this is actually come from where this Premier network come from. That's the question, the actual question, right? So this comes from cycles. Okay. So if you put here and underscore, okay, all cycles of this one. So it will give you the cycles here. Okay. And it will assign A to D and then D to C, this one, okay, and then C to B, okay, and then because this is cycle, so B to A, this one, okay, and then because you have two cycles, okay, and they are different and they are not repeating, so in that case we can add again with this B, D, C, so B to D here, and then D to C, D to C here. But D to C is already there, 1, so we add with one more, so become 2. Okay. Now, and then C to B, this one is already 1, so we add with one more, so become 2. Okay. So the Premier network.
Similar to the tracking trajectories.
Exactly, exactly. So, but this is done automatically. Okay. So the point is, why we can be sure that this is correct, because it really based on the actual structure, okay, of the network. Okay. How do you get that structure? One important point of irreducible, or strongly connected is you can decompose. Okay, you can decompose the strongly connected network into cycles, simple cycles. Okay, and then we can minimize finding these cycles and then assign these cycles. Then you will get exactly this Riemann network. So in the next hours, we can go to the detail in the network signature later. You can start to see the detail, okay, of this computation. So at this point, I want you to get motivated first. Yeah, the power dynamic here is just to show the application. Okay, later we will discuss about the theory behind. Okay, because if I talk directly the theory, you probably get confused. Why we are talking about this mathematics? Okay, then you will get bored. Okay, but once you understand how we will apply, then you probably get more motivated to understand the mathematics behind. Okay, so back to this slide. Okay, share. Okay, so go back to the slide. Okay. Once you have this power, okay, then you can start to see, oh, the father is actually the weakest here, right? Okay, so, and mother, son, and daughter have equal power. Okay? Then what happens if there is a new person here? So the structure changes. So when we do scenario analysis, you either change the structure or you change the strength. Okay, so here we have a new person, new agent, which is house cleaner. Okay, but this house cleaner is pretty smart. So she make a good friendship with the daughter. So friendship means two-way communication. Can you see? Okay. So, and of course, this is direct influence of the mother. Okay. Then we can, again, we just input, now become 5 nodes here. Okay. You put 1, 1, 1 to all. Okay. And then compute the premier network, you will get this exactly. Okay. So the new existence of house cleaner who make a friendship with the daughter. Okay. And then you can check the power. Yeah. Oh, very funny. Yeah. The father is actually the weakest. Even weaker than the house cleaner in this family, in this example of family. Okay. So, and because of this structure, okay, the daughter now become the most dominant in the family. Okay. And the son and the mother have equal power of 3. Yeah. Again, these numbers is not that important, but it's just the RAM that matter, right? But at the same time, the actual power give you certain understanding about the dynamic of this family. So you can apply this to your own family, right? So you can start to see what happened. But most important is there is a strongly connected network, yeah, in order to make that. And now, what if the father learn about management and now can influence everyone in the family? Yeah? Will his power become the most dominant or not? Okay. So again, because we don't know the actual strength, so we use premier network. Okay. So that way we add these new links. Okay, because the father now influence everyone in the family. Okay, so then we add this red links here. Okay. So then again, we can just input that into capacity matrix and then compute the premier network. Oh, now the premier network become bigger. Okay, no one in here. But if you want to see the actual strength, then of course you need to get the relative power. Okay, so in that case, you calculate the relative power there. If you look at the relative power, okay, the housemate is the lowest here right now. Yeah. So when the father learn management and influence everyone, yes, he is 33% higher than the house cleaner. Okay. But the mother actually now become the more dominant. Yeah. So okay, this is the power dynamic change because of how the influence changed in the family. Is it simple enough to do it on your own, right? Then, so one lesson we learned here is actually having more influence. It does not mean that you will become dominant. Yeah, the father here have more influence to all, but it doesn't make him dominant. So dominant power depends on the network structure, okay, and of course the strength of that influence. Okay. Then you will ask, how can I get the strength of the influence? Okay, that one is actually subjective. Okay, subjective. So in the next family, okay, here let's name this family P. Okay, this is almost perfect except the father have no communication with the son. So we have capacity matrix here. In this example, we know the strength. In the first family, family A, we don't know the strength. So in that case, we use premier network, isn't it? Because we don't know the strength. Okay, now we know the strength. So these are the strength. We can just put any ordinal number. Yeah, say 4 is the highest strength, and 1 is the lowest strength. Okay, so this is the strength that given. Okay, based on your own subjective thinking about the strength in the family. Okay, so just by inspection, this is actually very magic. Anyway, so we compute this, okay, and we compute this in terms of cardinal network and Premier, okay, and then we can start to see from the capacity matrix. Okay, this is interesting now. So the Premier network here is all 111. Okay, and then the cardinal network is somewhat very big. Yeah. So, but if you calculate the actual relative strength, okay, they are not. Okay, so this one is the relative strength of the cardinal network. So this is actually 1. The father is the weakest. Okay, and the son is also weak in this family. And the mother is actually almost 3 times of the father in terms of power. Yeah, this is not showing in the Premier network. Oh yeah, three times also. Yeah, but in here the Premier network, the father is like 2, yeah? And the son is also 2, right? So the Premier network is based on the structure. It does not know the strength. Okay, but when you know the strength, you will get actually better valuation. Okay, here is actually better valuation, right? Instead of 3 is actually 2.93. So you get more precise. Okay, instead of 3 also we actually 2 actually. So you get more precise when you have the cardinal network. Okay. So then we go to that is a base scenario. What happens if actually the father and son repair their communication? Yeah, so in this case, we add this red part here, the links. That means you repair the communication between father and son. Of course, now change the capacity matrix changed. Now here is empty, now become 1 and 1. This represents this 2 arrow. Okay. So what happened? Okay, when we include this into capacity matrix into Premier network and cardinal network, then you can see because this is based on network structure alone, full communication you will always get all the one equal power. Very nice. Okay, this is what it should be. Okay, but of course, in reality, cardinal network represent more reality than the ideal Premier. So in reality, you have power dynamic here. Yeah? This is actually 3 times than and this is actually 2 times than this 1. Okay. So in that case, the actual reality, the mother is still dominant. Yeah. Okay. And the daughter and the son is actually the second dominant, and then still the father of the weakest. Okay. But the communication become better in this second scenario. Okay, so we can compute the actual power, yeah, relative power. Yeah. Okay, father is 1, now 50%. A while ago, like 3 times. Okay, now become only 2 times. Yeah, the father the mother become less dominant when the communication between the son and the father repair. So who get benefit from this repair of communication? Yeah, the son actually get higher power. So in that case, the son have more benefit in repairing the communication with the father. Okay, so by just simulating very simple numbers like this, you can tell a lot of story, right? Yeah, see ya. Okay, so this one like 3 times a while ago. Okay. Now, oh, the daughter get higher power. Oh no, less power. Right? Okay. Okay, so improve communication between family will increase the power balance power, yeah, and reduce power domination. Okay, and we learned that cardinal network actually become more precise on the actual power than the Premier. Okay, and so just to learn about what is control. Okay, so then the father, knowing this, he tried to simulate, what happened if he want to become dominant. He doesn't like not dominant in the family. The structure is already communicate between father and son, but what is the cardinal, or what is the capacity matrix in order to make he become dominant? So in that case, he need to change the value of the power, okay, between family members in order to create that he will become the most dominant. You can try on your own, okay, and at least, okay, he need to add these values. Okay, instead of 1 now become 4. Yeah, earlier it was how much? 1, right? So now you need to make it into 4. So that's the question is, in order to make him to become dominant, DF and communication between daughter influence the father and son influence the father become higher. So how can it be? Yeah, so that means the father need to let the daughter and the son influence him more. Okay, that can only happen, okay, by spoiling the children. Okay. So in that case, probably the scenario 3 is not actually better. Yeah, if that is the case. So again, you need to interpret the meaning of this. Yeah, so that will create unhealthy competition between the father and the mother to influence their children. So in that case, if you are the father of the family and you know this is not good, then you will not do it, even though it increases your strength in the family, right? So again, simple numbers, okay, simple stories that you can create based on very simple graph. Okay, everyone have family, so you can always put that. Yeah. How about if I have the grandfather, the grandparent, the uncles, and so on? So you can always create the story within your own family. Okay, so we can also apply this in business. Yeah. So one of the question in business usually what is, can I run my business autopilot? Okay, and still run profitable on. Yeah. So the essential ingredient of autopilot is you need to add management. Okay, but if you just add communication between owner and management like this is not yet autopilot. Yeah, the triangle of owner, management, and auditor is actually the one that make autopilot. Okay? And then of course you need to include the customers, yeah, into this business model. Okay, so now you probably ask, how can I create the capacity matrix that include the strength of the influence, isn't it? So this is the theory. Yeah. So you practically include ordinal scale, any number. So in here, example 1 to 5, okay, that represent essentiality. Okay, that means how critical the link to the system's success or the integrity of the system. Okay, so higher number represent very critical. Okay? If this link fail, that the system is have higher risk of collapse or fraud. Okay, and 1 is nice to have, but not essential. But be careful here. Essentiality does not mean frequency. Yeah. So essentiality represent how critical this link if it fail together. Okay. So frequency represent periodicity. How often must use this link? So in the business settings, okay, frequency mean I need to control daily, I need to control weekly, or I need to control every hours. Okay, but essentiality represent how important it is. Okay, so this is the link can be high, essential, okay, 5, but low frequency. For example, I just audit every annually or every 6 months. Okay, but moderate essentiality but high frequency. So, for example, the manager will sending the short progress update to the owner or to the customers. Okay, so daily or weekly. Okay, so what you need to put in the value here is not the frequency but essentiality. Okay, so with that we can put any numbers that you think this is appropriate. Yeah, and you see here the meaning of each link you can also include. Yeah? So the owner will delegate his authority to the management, and management need to be accountable, yeah, to the owner, right? So the auditor will report to the owner, and the owner engage, yeah, the auditor. Yeah. So the auditor will instruct the management, and the management need to disclose the data. So this is the kind of monitoring system. Yeah. Of course, this management will sell a product or service to the customer and will get the feedback from the customers. Yeah. So with this, we can start to compute the, because we have the strength, so we can calculate the cardinal network. Yeah, both, yeah, cardinal and premier network. So now you can start to see here the name OMCA. Yeah? So that is I put there. So the management now become the most important role. Yeah? Based on the structure available, the management become the most important role. So you start to see that by throwing this network into irreducible, then you can start to see which one is the most critical. Okay, and when you put the values into cardinal network, you get more refined values. Yeah, so actually this is the most strength in the management. Okay, this is the base scenario. So what happened if in this example, okay, what I learned is the name business autopilot is actually misleading. Yeah. Business autopilot does not mean the owner no need to work or have no power to make decision, isn't it? Okay, it's only the frequency of the work is less often. Okay, but the essentiality is still there. Okay, so next is another example. Okay, which one is better? Okay, if the board decided that the customer must be the most powerful in the system, yeah, which one is better? Left graph or the right graph? Yeah, the left graph represents a customer direct feedback. So, and the right graph represents customer indirect feedback via the marketing. Yeah? So we have two proposals here, which structure actually give more power to the customer. Again, the links represent influence, control, and feedback. Okay. So to make it simple, so I put A, B, C, D here until F. Okay, so A represent management, B board, C customer, D production, E is sales, and then F is the product features. Okay. Then we put into numbers. Okay. So if you don't know the number, so I just put it into 0 and 1, and then I get the premier network because I don't know the actual strength. So once I get the premier, I will know that this is the actual important points. Okay, and this is the actual strength or the power. Yeah. So the customer here is have higher power using direct feedback. Well, in indirect feedback, you see the management and the sales have higher power, not the customer. In fact, the customer is just second most powerful. So this is what happened. Yeah, imagine the board is like the king. Okay. And the customer is like the citizen of the country. Okay. When the most powerful in the system never listen to the actual customer or the citizen, okay, so they rely on their ministers or their officer, okay, so sales is the officer, then practically the people is not the most powerful in the country or in this company, okay. So in fact, the management and sales become the more powerful here. You can see from these numbers, no? So interesting, yeah. So only a simple network, you can already get the insight about this. So this left graph with this direct feedback is actually more customer oriented than the right graph. Okay. So now the board decided we will use this left graph. Yeah. So direct feedback will be more empowered to the customer. Okay. Then rely on the report from the sales or marketing department. Yeah, this one. Anyway, so once the board decided to use direct feedback, okay, then the dynamic of the company changed. Okay. There is what is called office politics happen in that company. Okay. Again, people want to get more power. So then there are three proposals here. Okay. The base scenario is this one, the direct feedback. Okay. Now there is a three proposal. Oh, to make the product features, we need to have a two-way communication, or the production department will instruct the marketing or sales, or no, the marketing will guide the production. Which one is better? So facing this kind of power dynamics within the company, now you can draw and you can actually check the power dynamics. Can you see that? Okay, we have four scenarios. Yeah, the base scenario is the original. Okay, earlier. Okay, now we add two-way communication here, the red links here. Can you see? And then this is the production is higher than the marketing. That means the production will instruct the marketing. So I will produce something. The marketing need to do sales from this product. Okay, that's the meaning of this diagram. At the bottom here is the other way around. Okay, the marketing will get the feedback from the customer, and then the production need to create this product based on what the customer want of what the sales tell. Okay, or maybe two-way communication better. So before doing any computation, you probably say which one? You may guess. Okay. At first, I guess maybe two-way communication is better. Okay. So let's guess. Then we compute because we don't know the actual strength, so we use 0 and 1. That means only based on network structure, and we compute the premier network. Yeah. So then, if you look at the strength of the power here, then you can start to see. Yeah. In the base scenario, the management and sales. Yeah, the management is A, sales is E. Get the second highest power. Of course, customer is always number one here. Okay. So the production is important. Yeah, D is production, right? But if you use this two-way communication, okay, now that there is a change here. Can you see? There's a change here. Okay. Now the E actually getting higher. Okay. So when you create two-way communication, the power of the sales department compared to the base, okay, actually higher. Yeah. Okay. And the production now become as important as the management. Okay. So the two of them, the two departments now become a higher power. Okay. Now, if we do this production higher than the marketing, that means the production department will instruct the marketer. Okay. It's against the actual thinking that probably production will get higher power, right? It's not. Yeah, in this structure, okay, actually, it's the sales that get higher power. Okay? It's the sales that higher power. So what we want is not this kind of no power balance. Yeah. So to make it power balance, actually the best one is the last one. Yeah. So it is the marketing that's supposed to give instruction to the production department. Yeah. You see the power balance. Yeah. This is 2, 2, 2. Right. Can you see that? Yeah. So of course, customer must be the highest of 3. So now the management and all the department have 2, power of 2. Yeah. Except the customer is 3 and the board is just 1. That's okay. Clear or not? Okay. So by playing this kind of scenario, then you can start to tell the stories. This is the important part there. Okay, so what lesson learned here? Apparently the best power balance is to let the sales or marketing lead the product features. Yeah? It's not the other way around. So this is actually unexpected long-term effect. Yeah? When the production department leads the product features, to the marketing is actually empower more to the marketing department. And similar result also happen when both production and marketing cooperate to lead product features. So yeah, the point is now you can quantify. Yeah? Using this simple method, you can quantify, yeah? to understand the structure, the dynamic of the power, and to simulate. And of course, you can take control if you want to. Yeah. So with that, I hope this is good enough. You have assignment there, right? For this. Yes, you have question now. Yeah. So yeah, it's now you have informed decision, correct? Yeah. So in the next hour, we will discuss more mathematics. Yeah, about this. So you can also do this for politics, for projects, whatever. Yeah, the same. As long as you can put into notes and links, okay, you can just compute this. Everything just okay. Is there any question to here? Okay. So if not, I will just go to the next slide. Go to the slide of, oh, there's a question. The construction, yes. Construction you can also do. Okay. Yeah, I have it on computer. There are many case study about construction. Yeah, I think that the student did not make this yet completely. So, but there are several scenarios about construction management that we can also do. Let's go to the next topic, which is the mathematics of this. Okay, which is called the IFN signature. Okay, IFN signature. Is it? Can you see the screen? Okay. So yeah, the basis is basically cycle. Yeah. So this is the quote from the Bible telling that when you cast the bread upon water, after many days you will find it again. So everything it will turn back into cycles. Yes, in the assignment you can assume the network structure. Yeah, if even the strength of influence, you can assume no problem. Okay. So let me explain about this. This is like hundreds of slides, no? Okay, so I will explain several things in this slide. Okay, this is the next topic, right? So in here, I will explain that ideal flow is actually expandable network. Okay, and we can represent ideal flow as string, yeah, based on cycles. And then I will explain about network operator, which is assign and merge. And then there are two methods, okay, which is compose and decompose. Okay, and then based on this signature analysis, now you can start to understand what is the meaning of pivot. Yeah, so pivot analysis is basically you create the cycles, okay, and then you get the share, okay, between two or many cycles. Okay. And then, of course, because this is about mathematics, so the application is particularly about indices and the analysis of that. Yeah, from here we can get the integer IFN that used for power dynamic a while ago. Okay, let's start. Okay, so there are many terminologies in this slide. Okay, so I will mention it one by one. Okay, we have what is called cycles. Okay, we have a cycle matrix, linear equation, we have pivot, we have irreducible condition, we have two operators with this assign and merge, and we have two methods with this composition and decomposition. At this point, I understand it confusing, no problem, okay? And I start with summary. Okay, I will start with summary that will confuse you at first, but we will get back later at the end. Let's check whether you're still confused or not. Okay, so we start with what is called ideal flow network, F. Okay, this only happens if your network is ideal flow. If this is not ideal flow, you cannot do this. Okay, must be irreducible and pragmatic. Okay, then you calculate all the cycles. Okay, so, and then we canonize the cycles. Yeah, I will explain what is the meaning of canonize later. And based on the canonization, create the terms. Okay, the term is basically coefficient multiplied by the cycles. And then you have two operators, which is assign and merge. Okay, and then from this assign and merge, you can do composition and decomposition of IFN signature. Okay, so let's start with the first topic. Yeah, a network is called expandable. Okay, when the number of nodes and the links are formed as we assign the trajectory. Okay, so we start with an empty network. Okay, and then we assign the trajectory. Okay, the network is formed using the following simple rule. Okay, number one, if the link exists, then you add the link flow with 1. Otherwise, you create that links, okay, with that flow. Okay, simple rule. Okay, now when you create a links, okay, this also means that you create the nodes, okay, that support that links. This is different from the usual graph theory in mathematics, yeah? Where in the graph theory, link cannot exist without node. Okay, while the node can survive alone. Yeah, of course, this is still graph, and this is still the same, but the way we manage the operation is different. We manage by links rather than nodes. Okay, so why this is important? Yeah, so because of this, we can actually expand, yeah, the network in artificial intelligence. Yeah, So we can apply, okay, we can apply IFN into AI. Yeah. So one of the application, of course. Yeah. So in a moment, okay, I will show you how we will use this expandable network. Okay. And then we can assign the trajectory. Yeah. And then this concept alone will make actually the AI become AGI, yeah? Artificial General Intelligence. Okay. Right now, even the transformer, even the current AI is basically based on fixed size of the matrix. Okay, so using this concept of expandable network, you can actually make the size of the matrix or the size of the network expanded based on data. Okay, so let me show you. This is what is called mode choice, right? In transportation, we call this mode choice. Yeah, so this is the data of gender, car ownership, travel cost, income level. Yeah. So the first row represents the variables, and the second row represents the value. So in graph theory, okay, the node represents value. Okay. Now, if we want to apply, okay, IFN, okay, for machine learning or data science, then the node now become variable value. Okay. If you want to apply IFN into network automation, then the node become function variable value, action variable value, yeah, or function variable value. So the way you model will change everything. Okay. So because we want to create cycle, so I will create what is called cloud node to start and the end of the cycle. So now here we have gender male, so I will put the cloud node, okay, and then gender male GM here, and then the car ownership C0, so C0, and then the travel cost T chip, so TC, and income level I and low, so IL, and then come back to the Z, which is the cloud node. Okay, so this is the actual data for bus. So okay, so this is the actual data for bus. Okay, so what we do is we create this gender male as GM here as a node. Yeah, and then we have only two in gender, male and female, so GM and GF. Okay, the car ownership you have also two, C0 and C1, so this one. Okay, the travel cost in here is only one, which is cheap, so this one. And then the income level is low, medium, low and medium, so IL and IM. Okay, so because this is the class, so we don't put that, so we put everything here. So this is, now we read the data, okay, row by row, yeah. So GM, C0, TC, IL, so we assign, okay, with one. And then we read the second data, we assign again. So then we can get this IFN. Yeah. Is this clear how to get the IFN? So once you have this IFN, then you ask, so what for? Right? Okay, so I will demonstrate to you. Okay, what is this for? So let me go to the IFN lab in the Revolado a while ago. You can go there also. Okay. A while ago we were in the Premier network, right? So you go to index. Okay. You go to index IFN virtual lab. Okay. If you forget the page, you can just do QR code to this. Okay, and then what I want to explain to you about this trajectory, right? Okay, let's go there. Let's go to the last one. Here, can you see? IFN lab table classification supervised learning. Can you see? Okay. Now, the data have many. You can have many example of data here, but the first one is transportation. Okay. So I have how many? So like 10 data only in this example. So if you don't like this, you can create your own data and just copy and paste here. Okay. So this is the example of data. I have how many variable? I have gender, car ownership, travel cost, income level. So these are the 4 variables of input, and the output is transportation mode. Okay, because this is mode choice. Okay, whether you will use bus or train or car. So these are the 3 possible transportation mode, and these are the data. Okay, is that okay? So if you don't like this, for example, I can change this, for example, to mammal. Okay, so these are the other class, yeah, mammal. I have many data. Okay, or the golf, whether this is just telling whether this is good time to play golf or not. This is from the books, yeah, all this data. Okay, 2 classes on mammal, whether to buy computer or not, and so on. Okay, let's come back to the transportation mode. So when we read the trajectory a while ago, okay, one by one, okay, the node, then we can train this there. And you see, these are the 3 IFN for the 3 classes that we have, yeah, bus, train, and car. Okay, and here, because the name of variable is very long, gender, male, female, car ownership, one, and so on. So I make it has value so that easier to throw. Okay, so B1 in here, that means car ownership 1, yeah. B2 here represent car ownership 2, and so on. Is that clear or not? Okay, then you can predict the class. So given the 4 variables here, so I have random data. Okay, so if I have random data, I can predict the class here. So this data will predict class with certain confidence. Yeah, so I can change the data and see it will predict the class train. Okay, and then you can control. That control mean so IFN is basically generative AI. So that you can control, okay, by pressing which output. Yeah? For example, I want to see who are the people who use car. So if you click pressing this button, then you can start to see something that is outside the data. It can generate some data outside of the actual data above. Okay, so then you can start to see the pattern. Yeah, the one that use car is practically have a higher medium to high income level. Can you see? Right, regardless gender. Okay, and the car ownership should be, of course, 1 and 2. Yeah? And travel cost is always expensive. Okay, how about the bus? Okay, when you click this, and then you can start to see. Okay, so it's always travel cost is always cheap. Yeah. So based on generating pattern, okay, you can start to see the actual pattern from your data. Is this clear or not? Okay, this is the example of how we use IFN as expandable network. Okay, so that again, IFN is basically spatial directed graph where the matrix is irreducible prematrix. Okay, so you know, irreducible means strongly connected. Prematrix means the sum of inflow equal to the sum of outflow. Yeah. Now, the idea of IFN is come from you have a strongly connected network, okay, based on reading the trajectory cycles, okay, and then you assign that trajectory into the network, okay. So why we need to create cycle? Because random cycle in the random network would always form prematrix matrix, yeah, even with only single trajectory cycle, okay. But be careful here, okay? Assigning random cycle in the random network, okay, will not create IFN, okay? It will create prematrix matrix, yes, but not necessarily irreducible, okay? So when the network is expandable, then the flow matrix based on trajectory cycle always produce prematrix and irreducible if the cycle contain pivot. The pivot means there is some overlapping between those cycles. Okay, so these are the theory. So look at this now. Okay, we have a strongly connected network. That means we can always decompose the strongly connected network into cycles. These are the idea. Okay, and that means also if you have many cycles, you can always compose back into network. Is this clear or not? This is the main idea. Okay. A while ago, Vin was asking, right? Why we have two there in the premier network? Because we decompose the strongly connected network into cycles. Okay. So the theory of IFN means we have expanding network based on trajectory cycles. Okay. And it will always produce ideal flow network. So the question is, can we reverse the idea? Can we actually compose IFN into cycles that build the network? Okay. So to get this idea into practice, we need a new representation of the network, okay, which is based on string. So we go to the next topic, which is network as string representation. Okay. So as the background, last time we already did practice, right, in network representation, that you can represent network as directed graph or a matrix or adjacency list. So the challenge now is, okay, can the network also be represented as string? All right. What do you mean by string? String is just text. Okay? String is just text. So something like this. So if we have the string signature like this one, A, B, C, D plus 3, B, C, D, like this. So then the whole network, instead of typing all the network or breaking adjacency matrix or adjacency list, now become very short. No? The whole matrix, I can just put it as simple string like this. Isn't that more convenient? And this is more precise, in fact, yeah. So it's compact representation of network. Okay, and for human, looking at a lot of zeros in the matrix is a bit confusing and difficult to read. So in this case, if you can use a string like this, okay, it's easier to read by human. Okay, and because this is very small, just a few letters, then you can store and transmit, yeah, to say to other people, yeah. Storage is also part of it. And in computer science, okay, we have what is called regular expression, meaning string manipulation is super easy, okay, in computer compared to matrix or network. And then also there are many algorithms which based on string, yeah, the chromosome like evolutionary algorithm, like genetic algorithm, genetic programming, and so on. Okay? So then there's a problem. I can just represent node as A, B, C, D until Z, right? Okay. How many nodes can I represent? Okay, a small letter is 26, that I have only maximum 26 nodes, correct? And then if I include the capital letter, I have another 26. So maximum I can make is only 52 nodes, correct? But what happened is transportation network will have million of nodes, isn't it? Metro Manila alone is already like, I don't know, last time I downloaded the network is like more than 1 million nodes. Okay, so how can we represent the nodes as strings, a simple string like this, but we have millions or even more than 1 million. So then we need to do a different string representation, right? So then this is my proposal. Yeah, we can standardize the node name. Okay, this standardization is actually based on, yes, we can represent the numerical value in the strings. Yeah, so we can use what is called fixed length. So this is exactly the same like QR code. In the QR code, okay, you have a fixed length that there in the code, and then the QR is represented. Okay, so based on the same idea, so I created this. Let's name this phase-based prefix, suffix, or tier naming scheme. Yeah, so we have two parts. Yeah, prefix and suffix. The prefix represent the number, okay, of the suffix. Okay, can be 0, 1, 2, 3, and so on. Well, the suffix represent letter combination. Okay, so in phase 1, okay, there is no prefix. That means we have only single lower case letter. Okay, in phase 2, the prefix is 1. 1 is A, right? So when we put A capital here, yeah, that represents the fixed length of 1. That means after A, you get one letter, which is A to Z. So in that case, you have only 26. Okay, that means the number is 27 to 52. Okay, now when you put the prefix 2, the fixed length 2, that means B. Okay, so 2 means you have AA to ZZ. Is that clear or not? So if C, what will happen? You have 3 letters. Yeah? C means 3, right? So that means 3 letters after C. Yeah? If you put D, you have 4 letters after D. Yeah? If you have E, that means 5 letters after E. Is that clear or not? Okay. The whole idea of this standard naming of the node is so that you can create many nodes instead of just 52. Okay, using this, okay, I can create or say up to phase 27, right? With this Z. Okay, so how many nodes can we make with this kind of system? Yeah, extremely large. Yeah, we can create about 6 multiplied by 10 to the 36, which is higher than the number of stars in the observable universe. Yeah. Okay, so this is big enough. Yeah, simple mapping, but very big. Yeah. So with this, we can okay, you can practice. Okay. So you use IFN Excel add-ins. Okay. Create an index like this. Okay. create an index like this. So index and then put numbers, any number, say 1. And then you can put a node name. Okay, so this is the equal n underscore node name, and then go to that index. Okay, and then when you put node index, that means n node index of this node name. Yeah, this is just inverse function. So my question to you is, I don't know about your computer. Yes, theoretically we can go up to very extremely large, but in Excel you are not. Yeah, Excel have some limit. Yeah, so question: what is the limit in Excel in your laptop? Really different from each person. I don't know. Yeah. So yes, can you try this one? Yeah. So once you try this, we can understand the meaning of node names and node index. A few minutes, try. Is it okay? And then you show. So what is node name? What is, if your index is 1, what is the node name?
A, sir.
8. No, when your index is 1, your node name must be A, right? Okay. And when your index is 2, must be B. Okay. When your index is 26, it must be Z. Okay. But when your index is 27, become
Capital
AA, sir.
yeah, AA, yeah. So this one, yeah. So these are the guide. So if your index is 27, you get AA, a capital A and small a. And then 28 become capital A and small b. Okay, until 52, which is AZ. Okay. When you put your index is 53, now become BAA. Yeah? So okay, until the B is until here. Yeah. So when index is 104, you get B, capital B is represent 2 after this. So BZ. Okay. And then 105 is BCA. So this B now becomes C, and then Z now come back to A. So it's a combination. Is that clear? Okay. Until BZZ, right? That means 728. Okay. When you put 729, you will get CAAA, and so on. Yeah. I think if your value is just 1 million, I think is letter D is enough. Right. So the maximum is 27 letters. Very big. Very rarely you will use that anyway. Right. So with that, okay, maximum is 1 million. Yeah, if you get the numerical error, that means that is already the last value. Okay. Excel does not allow you to go beyond certain numbers. Okay. No. Okay, so in my case, I think I get this. I still get this, no problem. But beyond this, I cannot. In my Excel, yeah. Okay. So let's talk about cycle now. Okay. Cycle is just node sequence, okay, where the first node is the same as the last node. So remember, the node names is now represented as small letter like this, right? So Here we have only 3 nodes, which is A, B, and C, right? So without capital letter, that means the number of nodes is below 26. Okay, so then the problem is this kind of cycle have internal cycle. So from A come back to A and then can go back to B again and then go back to C. So there are many possible cycles inside the cycles. Okay, so this is not what we want. So what we want is called simple cycle or elementary cycle. What is that? It is a cycle in the network that does not visit any node more than once. Okay, of course, except for the first and the last node, which are the same, right? So this is an example, A, B, C, and then the last one should be the same as the first one, which is A. So what we are trying to get from the irreducible matrix or the strongly connected network are the elementary cycles. Okay, so simple cycles. So, and then that elementary cycles, we will put it into standard cycle name. Okay, this is what I defined as standard cycle name. So we call it canonical cycle. Yeah, how we canonize. Okay, is a unique string representation in the directed simple cycle constructed by rotating the cycle node sequence such that it starts with the lexicographically smallest node name. Okay, and then of course preserving the original traverse direction, and the last node is dropped. So I give you an example. So we have a cycle of A, B, C, A, right? Okay, so in that case, what we will do, we will drop the last node because when we put A, B, C, that's exactly the same as A, B, C, A. Is that okay? Yeah. So we drop the last node, but we remember this is canonical cycle. That means we still need to go from C to A. Okay. Now, if we have like this, B, C, A, D. Huh? So what is the first letter? What is the smallest node name? B, C, A, D. A, right? So in that case, you start with A. You see here. A, from A go to D. From D go to B, and then go to C. So there, the canonical will be A, D, B, C. Is it clear or not? Yeah. The next example here, you have D, F, E, C, B. What is the smallest lexicographical node name? Of course, B. So there you start with B, go to the first node, it is D, and then continue. F, E, C, like that. Is this clear or not? So we rotate. Yes, Franz.
Sir, how can you differentiate a cycle from the node names earlier? What if you have a very long, we have a node name of ABC or capital ABC? How can you know where it stops and where you are defining a canonical cycle or cycle?
Very good question. So we can that's why we have capital letter there. Okay. If your node name is very long, that's why you have capital letter. And that's why we have number of fixed length there. Okay. So if you have no capital letter, that means only single, no. Only lowercase letter. If you have capital letter, then that capital letter represents the next after the capital letter. What is the next number? So A means I have only one node. B means I have only two small letter here. If I have C, that means I have three. Okay, is that clear now?
Yes, I get it, sir.
Now you get the idea.
Okay.
You are very smart, so you can ask that question. Okay, so That's exactly the problem. Okay, how if we are very long, how can we get that? So exactly this is how we will solve. Yeah, using the capital letter. Okay. Non-existent capital letter, that means only A to Z. Existent capital letter. Now, what is the capital letter? A, that means only one. B mean only two after that. C mean three letters after that. So that is the purpose of the fixed length. Okay, clear, yeah? So with that, we can actually do this example. So you can practice this. Okay, this is exactly answering your question a while ago, friends. Okay, so suppose I have this cycle, very long, right? So my question is this one node, two nodes? How many nodes do I have in here? This is very long name. Okay, Kardi Teknomo, how many nodes? Okay, so okay, what if I have this? You can create your own, but anyway, let's do these 7 things. Okay, can you canonize the cycle string? This is the cycle string, right? So first you canonize, and then you can also get the total nodes, yeah, using this value. Just type in your Excel, okay, this one, and then you can practice. So when I put my name, no, so that represent one node. Why? Okay, K. What is the number of K, the index of K? J is 10, K is 11, right? That means after that you have 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 small lowercase letter, okay, after K. That means the whole name here represent one node. Okay, how about this one? BAA, ABDC, AC, yeah, BAA, AB, DAC. So first you need to canonize. Okay, so we start canonize by setting the this letter is the smallest, so this one, right? And then we can get the actual nodes, yeah. So because we have A, C, these are the one node. This is C is one node. BAA, remember capital B represent 2. That means after that is 2 letters. Okay. So and then capital A represent 1. That means AB is one node. And then D is another node. So these are actually 5 nodes. Is it clear or not? So if you have BADUT, okay, so then B and A, B is 2, right? That means A and D represent one node. Yeah? BAD is one node. And the next one is U and then T. So comparing the T, BAD, and U, so which one is the first lexicographical node, which is T. So this is the canonical value. Is this clear? Okay. So the color here represents one node. Huh? Up to here, is there any question? Yes, Lei.
How did you know that, like, for example, item 2,
Item 2.
how did you know that AC is not part of ABD alone?
How do I know that AC is not part of this one? Okay,
Yes.
okay. Let's start with, I will put drawing here. So B is 2, right? B is 2. So that means after capital B here, I will have 2 letters. A is 1, right? That means after A, we'll have 1 letter. This one. That means this is separate node already. And then this one have no capital letter. That means only lowercase letter. That means this is each of this is one node automatically.
Thank you, sir.
Clear, yeah? So this one is one node. Yeah. So how about this one? For example, number 5. This is capital. There is no capital letter. So this one is one node. This is one node. This is one node. Look at the capital letter. Okay. A is 1. That means after A must be one letter. This is another node. A is 1. So after this, only one node there. And once you put all the nodes, then you rotate to the, which one is the smallest? Of course, the smallest is A, yeah, this one, right? So then you make it into one. Anyway, the software help you for this, but at least you understand the meaning.
Thank you, sir.
Yeah. So 8 is how many 8s? 8, right? Okay. 8 here represent 8, so that means 1, 2, 3, 4, 5, 6, 7, 8. Oh, that means the whole thing is actually one node. Okay. Yes. Yeah. So is this clear? We are talking about the node name first, yeah, and then we canonize. Okay, so simple. Yeah, and next we can talk about signature now. Now this is the signature. Okay, signature is just a string representation as a formula, and this is just a simple linear combination of terms. Okay, so the matrix, this F must be ideal flow matrix, only ideal flow matrix. If normal matrix, capacity matrix cannot get, stochastic matrix cannot get this. Okay, only ideal flow network you can represent as string formula, which is amazing actually. Okay, so let's see. What is the meaning? Ci here, okay, is the cycle. Okay, Ci here is the cycle. Alpha here is the repeat of cycle. How many repetition this cycle need to be assigned? Okay, only that. Yes, only that. As simple as that. Okay, so this alpha times Ci that represent term. Yeah, you know, if you have for example 3x, that is the term, right? So and then plus 2y, that is also another term, correct? In mathematics, this is the name term is actually from the mathematics. So and you have numbers here, coefficient, okay, and then you have the cycle. Cycles is like a while ago, the node name a while ago. These are the cycles. Okay. And now from signature, you can compose into matrix, and then from matrix, you can decompose back to signature. Okay. So then the question is why? Why we need signature? Yeah. Because it's very convenient to communicate using signature rather than the matrix itself, number one. Number two, yeah, later we will compute very easily. You can get the total flow, you can get the total node, you can get a link flow, just simply looking at the signature alone. Okay, this is amazing. Okay, so and later also you can also do the cycle analysis. Okay, without doing the matrix, you can start from the string alone. You can already know the meaning of this. This is the one that very strong representation. Okay, so let's go to the IFN virtual lab in level 2. Okay, but before that, I will explain about this. There's a new graph. Okay, you can see there in IFN virtual lab. It's called signature graph. Okay, something like this. Okay, so the signature itself is just like this, right? ABC plus 2ADB plus C 3CD, for example. These are the signature. Okay, and from this signature you can create a matrix, you can create the graph, but there is another graph called signature graph. So what is this signature graph? Signature graph is representing the cycle in the node. Can you see this is CD, this is ABD there, and then ABC there. Okay, and then it will connect the pivot. Yeah, the one in orange there represent the connection between cycles. This represent the pivot. You see, pivot means the sharing of the node or links or path. Okay, so here CD, this one is ABC. Of course, the pivot is the one is repeating with the C, right? So the pivot is C. Can you see this? Okay, in here ADB, and then this one is ABC. The pivot is the one that repeating, yeah, with this A and B, yeah. Okay, the same thing CD and ADB. The pivot is D. Yeah, pivot means the overlapping, okay, between cycles. So this graph will make it easier for you to do pivot analysis. Yeah. Of course, you can directly get the pivot if you want. If it's very small number of cycle like this, no problem. Yeah. But when the cycle become very big, so you probably want a graphical representation. Okay. So let's go to the lab first. Yeah. Let's go to the lab. I will discharge this one. There. We go back. Can you see the virtual lab here? Okay. Can you go here to the IFN lab composition decomposition? Can you go back? And then go to IFN lab composition decomposition. Here. Okay. So the explanation is just there. Okay. All the one that I want to explain, but you can read by yourself. Okay. Let's do the practice lab. Yeah. So when you click this one, and this orange is this random signature. So you just press this, it will create random signature. Okay. So this is the random signature that, of course, you can also add. No? So for example, I can add with AB. Okay. So you just type there, and then you can press this arrow button to compose. Yeah. From signature, you can create the matrix. Yeah. Of course, you can also see the matrix in the pattern or the actual graph. Yeah, directed graph here. Okay. And the signature graph is just below. Okay, the signature graph is just below. AB here. So these are the pivot. Yeah. So if it doesn't work because you change, you can just generate the graph. Okay, and you can also export as PNG or GVG, or yeah, this is just to download. Okay. So in here you can also have a lot of operation. So you can check if this irreducible cycle or not. Yeah. For example, if I put it this way, I put GH, okay, and then check whether this is irreducible. Is not. Okay. Based on signature alone, you will know whether it is irreducible or not, whether it is premier or not. Yeah, whether it is. We can do a lot of operation here. You can get the total flow based on this alone. Yeah, on the string. Of course, you can also get it from the matrix. Yeah, so okay. Once you get the matrix, you will get the same thing. Yeah. So you can, from the matrix, you can get the total flow, exactly the same, right? A while ago, I did not even calculate the matrix yet. I can get from the signature. Okay. Let's do this. So you can practice. So you can also add. Okay, you can because this is not irreducible. That means reducible. Why? Because they are not connected. Yeah. So this is clear in. You check here. Not irreducible. Yeah. And then is reducible, not irreducible. Yeah. Not irreducible because they are not connected. Yeah. So be careful. You create a cycle here does not mean that it will create IFN. Okay. Only when there is a pivot. So you check here what are the pivot. So the pivot is A, C, and D. So that's why it doesn't share pivot in E and F. Right? So there you see EF there is no pivot. Yeah. In the graph there is no pivot. So the graph alone you can see there is no pivot. That's why this is reducible. So something is wrong with your system. Okay. Okay. So from here you can easily create random network signature. Yeah. Depending on the size that you want. Yeah. You can create, and then you can also add. Yeah. You can add new term in the signature. Okay, you can add 2, for example. You can also add these other possible. Then there you can add that 2 A B C D E, right? So I add that. Okay, then you can just click this to create the matrix and the network. Yeah, of course this is very complicated. This network you can use control key and then you can move it around. Yeah, you can move it up to make it to see it better if you want. Okay, so let's come back. With the tools available for you, you practically can do from network signature to the matrix and from matrix back to the signature, isn't it? There. Is that okay? Any question about this? So if not, let's continue. The tools is given to you already. Yeah. Yes. Signature is aesthetically pleasing. Yeah. So now, these are the properties of signatures. Yeah. Cycle can be canonized. Okay. So you see that B, D, so this is C, B, D, A. That is actually the same as A, C, B, D, right? This is the canonization. Okay. Or this cycle is also the same. So this are the cycle combination. So if you look at the web a while ago, you can see the actual permutation here, okay, of the cycles. Yeah. But if you canonize here, this is the canonized, suddenly the number of cycles is actually smaller. Okay, let me go to the simpler one. Maybe 4 is better so that you can see. Okay, so this one, okay, if you canonize, okay, this was still a lot. Okay. Okay. Let me go to the previous premier network so that you can see. This is the capacity matrix. Can you see? And when you get the cycles, okay, you have only 2 cycles here. In this matrix, capacity matrix, you get the cycles. Okay. So if you don't canonize, okay, you will get, these are all the cycles that you have. Permutation. Okay. But when you canonize, okay, so you see here ACB is actually the same as CBA, isn't it? Okay. So the same as BAC. So in that case, become 1. Canonize. Can you see that or not? Okay. If you don't canonize, you will get all the combination of cycles. okay, which is a law. Okay, but when you canonize, suddenly things become simpler, only two. Okay, that's why we canonize, so that you get the standard name easier. Okay, but when you compose or decompose, not necessarily you get canonized. So that's why we still need this canonization. Okay. Next, let's come back here. Okay. The term of the same canonical cycles can be added. So these are the same, right? This is the same cycle. This is a permutation of the same cycle. So then if you add this, it will just get the same as this one. Yeah. So CBDA, this one, which is the same as BDAC. Okay, when you add, it's exactly the same as the canonized this one. So you can add, become 2ACBD. Okay, so if they are the same cycles, you can add the coefficient. Similar to mathematics, as simple as that. Okay, so 2 plus 3 is 5. If they have the same term, okay, coefficient of the same term, you can add. Okay, and coefficient for all term can also be multiplied or factor out. Okay, so for example here, okay, 3 ACBD and then 6 ABC, right? So because 3 and 6 can be factored out with 3, so you can put it 3 multiplied by, okay. The software cannot handle this, but in Excel you can multiply. In that virtual lab, I still did not make it. So the order of the term is also doesn't matter. Yeah, so you can reverse the order, no problem. Okay, and what's the meaning of single letter in the cycle? Yeah, the single letter represents diagonal entry. Yeah? So example here. So I have example A, B, C, D. Okay, look at this. So this is how you assign. Yeah, AB, this one is AB here, right? So you put multiply by 2. So you put 2 here. And then the next one is BC. So this one is BC. So you put 2 here. Okay. And then the next one is CD, right? So this one is CD. So you put 2 here. The flow, you put it there. And then the last one is DA. Be careful. This is a cycle, so you need to come back from the last one to the first one, right? So DA, that one, DA. So there you get the cycle by assigning the first term. Okay, how about the second term? This one I have coefficient of 1, so this one is 1. Okay, but C, what's the meaning of C? That means CC. Yeah, from C to C. That one is meaning diagonal entry. Clear? Okay, you see, yeah? Okay, so with this, you can check, yeah, from signature to matrix, yeah, matrix to signature and so on. So you have the software. You can also do manually if you want. Okay. So next, I want to discuss about the operator to assign and to merge. Okay. So remember, IFN is an expandable network. That means we can have two main operator. Okay. The main operator is related to a while ago. One is called assign, and this is actually based on transportation ideas of traffic assignment. Okay, exactly that. Okay, so what we assign here is not just the link, but the cycles multiplied by the coefficient. Okay, so we assign, okay, when we said assign, is we assign the cycle. That means every 2 nodes become the links, you put it a flow. Yeah. What is the flow? The flow that you assign is alpha, which is the coefficient. Yeah. So when you assign a cycle, you will create a flow matrix. Okay. And interestingly, initially you have empty flow matrix. So F0 here is empty, meaning 0, 0, 0, 0. Yeah. So, and then you assign with this term, with this alpha times K. Okay. Then you will create a flow matrix of index K. Okay. And then you merge. Okay. Merging is the same as addition of matrix. What's the difference between merging and addition? In matrix addition, okay, the size must be the same. In merging, the size will expand. Okay, I will show you in the moment. Okay, the example of this. Okay, don't worry. So when we said signature is basically assignment and merging. Okay, so when we said unit assignment, that means the alpha is just 1. Okay, this is where we will create a premier network. Okay, initially F0 is 0, all matrix of 0. Okay, so when we said basic assignment, that means you assign a cycle to the 0 matrix with the flow of alpha. Yeah. Okay, so this is the theorem. When you assign a cycle, it will always produce prime-magic matrix. Remember, prime-magic matrix is not necessarily IFN, okay? It's just prime-magic. So this is an example so that you will see. Yeah? Say I want to assign cycle A, B, C into an empty network. So initially you don't have network, and then empty network is basically 0, 0, 0, 0, all the matrix is 0. Okay, now you assign A, B, C, which has 3 nodes, right? A, B, and C. Okay, so now the 0 matrix, because you have 3 nodes, so you create 0 matrix size 3 by 3, like this. Okay, and then you assign. Now, cycle ABC, that means trajectory is A to B to C and to A, right? Remember, this is cycle, canonical cycle, that means from C come back to A. So then you separate into links. No? So A, B, B, C, and then C, A. Okay? Then you assign. So A, B, you put there 1. B, C, you can put there 1. And then C, A, you can put there 1. And then the network become like this. Clear, yeah? Okay. Next, you can practice. Okay. Or can you assign A, C, D, B? Okay. What will happen if you assign A, C, D, B? Okay. So first you create empty network as 0 matrix. Okay. Remember, A, C, D, B have 4 nodes. That means A, B, C, D. Okay. That means the 0 matrix must be size 4 by 4. Okay. What is the flow matrix? Is it prime-magic? Is it irreducible? You want to practice? You want to try? So that you can get the idea. Yeah, you can show us a recitation. Okay, thank you, Queen. Yeah. So the answer is already there in the slide also. You can start to see. So when you have A, C, B, D, okay, that means the trajectory is from A to C to B to D and then come back to A, right? So then now you separate them into links. So you have AC, you have AC, CB, and then you have BD, and then you have DA. Okay? Then you assign this. Okay? So yes, this is very magic. Is this irreducible? Yes, it is also irreducible. Yeah. Okay, correct. Yeah, correct. Magic and irreducible. Yeah. So next, now we merge. Okay, the second operator is merging. When you have two network, not necessarily IMN, okay, and then you merge them by adding the link flow. Okay, so the size expanded to the highest. Okay, yes, very good. Yeah, ladies and gentlemen. Okay, so the size expanded to the highest. Okay, let me give you example. So consider assigning a cycle C1 with alpha 1 unit, okay, to empty network. So F0 here is empty. So you get F1. And then you assign again C2, okay, cycle C2 with alpha 2 units of flow to the empty network again. So you get another flow matrix, F1 and F2, right? Now you merge them. Okay, when you merge them, that is equivalent, this 3 bar here, that means equivalent to you start with F0, you assign with cycle 1 and alpha 1, and then you get F1, right? And then you assign again with alpha 2 and C2, yeah, to get F2. Yeah, so that is the meaning of merging. That means you can actually create a difference equation here, yeah. So when you create assign and merge, that means you assign from the previous one, go to the next one. Yeah, so that's the same as you assign from 0, okay, repeatedly up to K. Yeah. And for you, probably this is not so important. But let's see the example. Okay. So a while ago, we already created ABC and ACBD, right? So that one is F1 and F2. They are not the same size. Okay. So when you merge, what you will do, you create the size which is the largest. So, okay, and you combine. Okay. So you have A, B1. Here you have A, B is 0, so you still have 1 here. You add. Okay. And then you have BC1, so BC1 here. So here is 0, so you can add 1. So this is just combination of the two. Yeah. In Excel, you can use this. Okay. You can assign term, okay, assign, merge, and so on. So you can actually create say you start with signature, something like this. Okay, I start with signature like this, and then you can signature term. So that means I will get term here. Okay, and then here is term 2 cycles. That means I will get from the term 2 cycles. Okay, so this is just to get the cycles. And then here is the coefficient. That means term 2 coefficient that from the term. So from here, I can get the coefficient. Yeah, this is the term, so I get the coefficient. So if you want to separate them, so you can. Yeah, in Excel, you have the function. Yeah. Now, after that, you can assign a term. Yeah. So I have 3 terms here, 1, 2, 3. Right? So I can assign the term, the first term to F0. And this is the F0, 0, 0, 0. Right? And then I can assign the second term and the third term to F0. And then when we have F1, 2 here, that means you merge F1 and F2. Okay? And then you can also assign term 2 to F1. Yeah? Then you can start to see the difference. Huh? And the last one here, F1, 2, 3 is you merge F1, 2 here with F3. Yeah. So this is final one that you can. So that means you can actually see, okay, from signature, this is what you do to compose the matrix. That's the meaning. Do you got the idea or not? The idea is you have the signature, you separate them and then into terms, okay, into cycles and coefficient, and then you assign them one by one internally. This is the internal work on that, yeah. And then you will get, and you assign and merge, you will get this matrix finally, okay. But of course, you can also use directly, yeah, without all these steps. You can get directly compose. So you can use signature compose, yeah, means the input is signature, then you can get this matrix. You want me to show? Let's open the Excel. So what is the signature there? A, B, C plus
Plus 2BC. Plus CE.
plus what?
2BC. 2 boy.
Ah, 2 BC, right? Plus
Plus
EA. Okay, so that just type the string, okay? And this is the 3 by 3, so we have so if you want to get directly the matrix, you just n underscore compose the compose of this signature, okay, yeah. And then this is 3, right? So you have 3, 1, 2, 3, yeah. Again, you press Shift Control Enter, forget that, and you get the matrix of that signature, yeah. It is exactly the same as this one, yeah. So from here, of course, you can get back, yeah. So you can do n underscore decompose. That means you have the matrix, okay, and now I want to get the signature. Yeah, I can get. This is exactly the same. Yeah, just different format, right? This is more standardized format. Clear or not? Any question? Yeah. The term and the assign and merge is just the operation inside, okay, to get this so that you will understand. So what happens if we have, okay, this is the actual practice that you need to do. Can you assign cycle A, B, C, and D, E, F, G, and then merge them? Yeah, I have no answer here in the slide. If you have two cycles, A, B, C, and D, E, F, G, what is the flow matrix? Is it premagic? Is it irreducible? Okay. So now I can change this. Okay, so I change this into A, B, C plus, what is that? D, E, F, G. Oh, this will not work, so because this is 3 by 3, right? Wait, I will create a new one. So A, B, C plus D, E, F, G. How many nodes we have?
7.
4, 5, 6, 7. Okay, so let's do 7. Okay, so I will prepare the 7 matrix. 3, 4, 5, 6, 7, yeah. 3, 4, 5, 6, 7. So I prepare here. Okay. Then I will put here n underscore compose, right? Supposed to be. Okay, compose of this one. Let's try what will happen. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, let's do this. Oh, so you get the matrix. Yes, you can, but this is not okay. You can start to see is this wait, n underscore is premagic? Yes, supposed to be premagic. Okay, premagic, yes, it's supposed to be premagic. Yeah, is this irreducible? N underscore is irreducible? Okay, check. Is irreducible? No. Of course not, right? Yeah. Okay. Why this is not irreducible? Because there is no pivot between the two cycles. Can you see that? Yeah, A, B, C. So there is no pivot. Yeah. So then this is not IFN. Yeah. The result is not IFN. Yes. Okay. Clear, yeah? So you can still create the compose, but you will not get IFN, yeah? So you can get IFN only if you have the pivot, yeah? So you can get the pivot from here. So N underscore a signature to pivot, yeah? There, signature to pivot. Yeah, you have the signature and to pivot, then you will see nothing, yeah? That means no pivot, okay? Is it clear? So if I want to create pivot, I need to add something that repeating. For example, here, I can create D, E, for example. There, the pivot is D, E, D, and D, E. So you have pivot. Is it clear or not? So what's the meaning of pivot? Yeah. If you have two cycles, okay, pivot means they are sharing the same node, yeah, either link or path. Okay. So imagine this is a network represent you and your girlfriend or boyfriend, okay, and these are or your spouse, okay. This represent the pivot represent the events, okay, where you are actually together, sharing, yeah, sharing nodes. If the node represent the events, then these are the events or the moment that you are sharing together. Yeah, I hope you understand the meaning of pivot here. Okay. So come back to the slide here. So basically you can create integer IFN. Okay. Remember that. Now based on this, you have the signature, then you can always create integer IFN. Okay. Last time we talked about IFN, it's very difficult to get the integer, isn't it? You need to do LCM. Yeah. Okay. So you probably need to do the fraction first and so on. But using signature, automatically integer. Okay. If you have at least one pivot, then you can get IFN. Okay. So this algorithm you just ignore. So let's take example, yeah. So if you have this A, B, C and 2AB, so basically A, B, C is A to B, yeah, B to C, and then C to A, right? So these are the three. And if you have 2BC, that means from B to C and then C to B, yeah, these are the two. So the two here is a flow that you can put in, yeah. Then you merge them together, so you get this matrix as the composition of the signature. Yeah. So if you want to practice, you can practice this. Okay, we have many example of signature, then you can compose. Yeah. Okay, so let's go to the next point. Yeah. So if you want to test in the matrix, okay, if you want to test in the matrix whether this matrix is irreducible or not, wow, you need to exponent that matrix. You need to add first with the identity matrix, and then you need to exponent that matrix n times, yeah, minus n minus times 1. Yeah? N is the size of the matrix. Imagine if your matrix is very big, so this alone takes a long time. That's why if you use IFN transport, sometimes it freezes to calculate the irreducible or not. Yeah, because if your network is very big, yeah, this one is the n exponent. This computation is extensive. Okay, so now what happened if we use signature? Okay, when you want to use if you use just signature with this only strings, okay, to get the pivot, okay, if you can get the pivot, which is the overlapping node name, okay, if you have the pivot, okay, between any two terms in the signature, then your network is irreducible, as simple as that. See, string representation actually help a lot, okay, in solving computational problem in here, yeah. So in this example, okay, I have ABC plus 2DE. There is no pivot, okay. So when you form the matrix, clearly this is reducible, yeah. Reducible is by definition is this form with 0. Okay? So this is practically a reducible matrix. Okay. So you can practice, you can generate random cycle and then combine the signature, and then you can compose the signature, and then you can practice to test, yeah, whether this matrix is pre-magic or reducible or not, and then test the signature is reducible or not, and then you can show the list of pivot, yeah, the one that we just I just showed a while ago, yeah. These are the lab session that you can practice at home. Okay, next, now you have the signature, you have the matrix, say integer IFN, you can actually form the signature type, yeah. That means the way to compute is actually called unlearn. Unlearn is assigned with negative value, and then you merge. Okay. The algorithm you can read by yourself, so basically just unlearn this. Okay. So again, the algorithm is not so meaningful for you. Okay? For the computer science problem, this is important, but for you not, right? So I just skip that. Okay? But for you, you can start to practice this, yeah. So you generate random ideal flow and then find the signature and then try to decompose it, yeah. With negative assigning negative coefficient if you want, so that you can understand the meaning of the decomposition algorithm. Okay. Now, this is what you need to understand, and this is the one that you will do in the next week quiz. Yeah, next week we have quiz on this. Okay, so that you can read again and understand. So here it is. Yeah, two signature is called identical when they come from the same canonical cycle and they produce the same ideal flow matrix. Okay, so this is an example. Okay, say you have these cycles, okay, and the two of them actually have the same canonical cycle of this one. So in this case, these two signatures are identical. Okay, remember, yeah, identical means they have the same canonical cycle and the same ideal flow matrix. Okay, look at this example here. I have two BAC. It is actually this one. CAP is the same, right? And then I have BC, yeah, which is the same as CP. I have AB here, which is the same as AP, and then I have DP, which is the same as BD, right? Canonical cycle is the same. Okay, so in this case, the two signatures are identical signature. Anyway, you can check in Microsoft Excel. Okay, identical signature. You can also canonize it, right? So let's practice this first so that you can create any random signature for this one you can use. And can you test whether they are actually identical or not? In preparation for the quiz next week. Yeah, they are identical. Okay, good. You see, yeah. So next term is called equivalent. What's equivalent IFN? Yeah, equivalent IFN means the two signatures are called equivalent when they produce the same ideal flow matrix. Okay, but they may come from different canonical cycle. Okay, so this is an example. If you have this two signature. Yeah, identical. Yeah. So if you have these two signature, then you check. Yeah, this is A and A. This is B and B, 3B, and then this is BD. Oh, there is no BD here, right? This one is four terms, you see, four nodes, A, B, C, D. In here, there is no A, B, C, D, right? So they are different cycles, okay? But the two of them produce the same matrix. So in that case, they are equivalent signature. Okay? Of course, identical signature always equivalent, yeah? But equivalent is not necessarily identical, right? Okay, so this is an example. Yeah. So if you see here, I have four nodes. In this one, I have three nodes. In here, I have three nodes, and then two nodes. Okay, but when you check, you compose, yeah, from this signature and you compose from that signature, you will produce exactly the same matrix. Yeah. So in that case, they are equivalent signature. Clear? Okay, so the same thing, test. Can you test whether this signature are equivalent or not? Yeah, the green one and the blue one. Yeah? So the green one you put compose into matrix, and then the blue one also you compose into matrix. Okay, they are not the same matrix. So you can put n underscore equal n underscore, okay, is equal matrix or not. Yeah, they are not equal matrix. Then, of course, they are not equivalent. Okay. Okay. So, okay, can you do this practice? I think 1, 2, 3, 4, 5. Okay. Any of you? Mhm. Yeah, this is A, B, C, D, E. Yeah, this number 3 is clear. Yeah, identical. It just refers the order only. Yeah. So please check. Okay, you just do is equivalent is identical signature. Yeah. So yeah, is equivalent signature, is identical signature, is equal matrix. Okay, and then you can also create random equivalent signature. Yeah. Yes. Okay. So you can start to check. Yeah. With this, we please come on time next week. Okay, and then we will start the quiz. Just 10-minute quiz, yeah, about this equivalent and identical signature, and of course the power dynamic. Yeah. Please read the 2 slides. Okay. So let's do some application, mathematical application of this signature. Okay. So using signature, you can get the total flow, total node, link flow, and so on. So I will just show you a few of them. Yeah. Okay. This one. Look at this. I can get the total flow from signature simply by looking at the signature and count the number of nodes and then multiply by the coefficient. Okay, this is the formula. Kappa is the total flow in the network. Okay, if I know the signature, I can just get the number of nodes in the cycles and then multiply by the coefficient. Okay, and then you sum. Let's see the example. Oh, here, ABC plus 2AB. How many nodes in ABC? 3 nodes, yeah, A, B, and C. How many nodes in A, B? Cycle A, B, 2 nodes, yeah, A and B, right? So, and then this one is 3. So, get that. Fine. So this one is 3, okay, plus 2 is the coefficient, right? Multiply by this one is 2 nodes, so you have 2. So the total must be 7. See, the total is 7. You see. Nice, yeah. Amazing, right? So simply by signature alone, you can get the total flow. Huh? So again, okay, how about this one? Okay? Can you get the total flow? Yeah, I have very long, okay, if you look at the matrix, quite complicated, yeah. Okay, but look at the signature, okay. So this one is 6 multiplied by how many? A, B, C, D, so 4, right? Plus, yeah. How about this one? 8 multiplied by 3 plus 10 multiplied by 2 and 7 multiplied by 2. Yeah. So and then you sum all of that, you get 82. You can just compute by yourself. If you compose that, and then you will get exactly the same combo. See, from interesting, yeah. So from signature, from string alone, you can get the total flow. Reading string, you can get the total flow. It's like miracle, right? Okay, the same thing here, yeah. So can you get the total flow of this one? Yeah. So again, you can simply 3 times 1 plus 1, it is 4, plus 3, so 7, plus 3 again, 10. So this must be 10. Okay. Yeah. So the same, yeah. They are the equivalent signatures of this must be the same. Okay. So to get the node flow, okay, you need to understand the meaning of chronicle delta function. Yeah? Chronicle delta function is very simple. Look at this. If I have delta x, if the x is true, then make it 1. If the x is false, then make it 0. That's it. Okay. So to get the node flow, all you need to do is to get the P if belong to cycle or not. If true, then 1. If not, 0. Okay, and then multiply by the coefficient. I give you example. Okay, so here I have A, B, C, and 2AB. I want to know C. What is the node C? What is the flow in node C? You check in here C, how many? C is only 1. Here there is no C. So that means C is just, the node flow of C is 1. How about this one? B. What is the node B here?
3.
Yes, 1 plus 2, so 3. Okay. How about node A? 3 also. Yeah, super. You're very good. Okay. So super easy, right? Okay. So you can also test, okay? You see the matrix, and you can get the sum of row, sum of column. Yeah, it is the same. Right? So because this is ideal flow matrix, but you can also get it directly from the signature. Yeah, without the making the matrix, you can also get. Yeah. So for example, A. Yeah, supposed to be 6, 8, and 10. That is how much? 24. Is that correct? 24. Let's check that. A is 6A, you have 8A, you have 10A. So see, exactly that. Okay, 24. Yeah. So the signature that represent the matrix. Okay, the node flow. Okay. The same thing, if you want to get the link flow, which is the entry of the matrix, you can also do that. Okay, practically you just put whether with the chronicle delta, whether the link PQ is in the cycle or not, and then put it as 1 if it is true and 0 if it is not true. Okay, and then multiply by the coefficient. That's it. Okay, so the same here. If you want to know, for example, link this one, yeah, 13, right? What is this? BC, yeah. So you go this here, BC. Here there is no BC. Oh, this one have BC. So the coefficient is 7. This one coefficient is 6. So 6 plus 7 is 13. Exact. Okay. So this one is 0. This one is 0. What else? For example, I want to check this one. AD. Okay. Where is AD? Oh, this one, 10. Yeah. This one is DA. Yeah. So DA is interesting, yeah, because now you have DA, which is come from this cycle, 6. Right? This one is D to the A. And then this one also D to the A. And then this one also D to the A. So you have 6 plus 8 plus 10, which is 24. Is it clear or not? Okay. So with this, you can, of course, you can do the lab session also. Yeah. So from here, of course, you can get all the integer IFN. Yeah. The one a while ago that I explained. So this is the one that important for you, right? Application is about power dynamic and so on. But what is premier IFN? Yeah, premier IFN means this is based on the minimum integer based on the input of the adjacency matrix. Yeah, 0 and 1 only. Okay, so premier IFN actually the basic building block of any integer IFN. Okay, so if you have this is the capacity matrix. This is the stochastic matrix. If you find the premier IFN, okay, then you will get a different stochastic matrix than the capacity matrix. Yeah, can you see? The premier IFN is not the same stochastic matrix. Okay, so in fact, this is the minimum integer. Okay, yeah. So with this, you have the assignment, and then you have the quiz. Yeah, in the beginning of next week meeting. Yeah. So with this, you probably get the idea now. That this is the summary. You have the F, ideal flow matrix must be, and then you can put it into cycle, canonize, and then you get the term, and the operator are assigned and merge, and then you can compose, okay, to get the event signature and decompose back to the matrix. Yeah, and these are the examples in infographics. Yeah. So what happened? What happened is this. Can we actually create similar to signature, but not only IFN, but for others? Yes, we can. Yeah. If we don't use cycle, but we use path, for example, we can actually use also. Okay. But I haven't make it yet, so maybe you can make it if you want. Okay. So in summary, signature is a convenient way to represent the IFN as a string formula. So you can just compose and decompose. And then you can also get the minimum integer and based on this. Okay. And be careful. Irreducible matrix can be decomposed into cycles. These are the basic idea. Okay. And then when you assign only the cycle to produce, it will produce very basic matrix, but not necessarily irreducible. Yeah, can be unconnected network. So if you want to compose IFN, this cycle must contain P4. Okay. So of course, now if you have the IFN already, then you can always find the P4. That's the meaning. Okay. With that P4, you can start to see what is the most critical points in your network. What is the most critical links or nodes or path in your network? Okay, that is called pivot analysis. Okay, thank you for today. I hope this is clear.
Thank you, sir.
Yeah. You have any feedback before we leave or question?
Sir, just to reiterate, the quiz will be this
Two
all the
slides.
subjects.
Yes.
Sorry, again.
The two slides. The
the two
power
slides.
dynamic, and the F and signature.
All right, sir. All right. Okay.
Only two
Thank you.
questions. Anyway, and it's only two questions. Multiple choice.
Terima kasih.
Multiple choice and 2 questions. That's
Only
good.
two. Yes. Okay. The quiz is only 10 minutes, so please come on time. Okay. The reason I allow to have in the midterm exam, even the final exam, to have online, okay, one whole day from morning until evening, because even if you ask AI, it will not answer to you. Right? Because this is new thing, so I don't think AI knows about all of this. Right. So, okay. So that's why no problem. Even if you use AI, AI will not answer for you. So you need to understand all of this material anyway. Okay. Good. So I hope this is useful and interesting enough for you. Okay. So if you have any question, if you want to have a consultation, so go ahead and ask me in the email or in the Viber or in Facebook. Yeah. Thank you.
Thank you, Doc Kardi. Good evening.
Thank you,
Goodbye.
Dr.
Thank you.
Kardi.
Thank you,
Bye.
sir. Happy
Thank you,
weekend.
sir.
Thank you, sir. Good night.
Thank you, sir. Good night. Good evening.
And